how to find bottlenecks in ClickHouse. We'll talk about tools, patterns, and simple steps to find and debug slow queries. My goal today is provide you a clean approach which you can use after this talk. Who am I and why I can talk about this topic? My name is Eugene Klimov, my nickname is Sledge. I worked in IT since the last millennium. Actually, this is my first public English talk. I hope it will not terrible as I expected. Most of the time, I prefer another very languages. In the last 5 years, I worked mostly full-time with ClickHouse. I maintain and contribute tools like ClickHouse Backup, it's a backup solution for ClickHouse, ClickHouse Yerevan, it's a data source plugin which allows show us ClickHouse data inside Yerevan. ClickHouse Operator, it's our alternative solution to deploy ClickHouse clusters inside Kubernetes clusters. And last but not least, it's alternative MCP, it's AI-based tool which allows you to integrate your LLM agents or your LLM chats applications with your ClickHouse database. You can find my work on GitHub account on github.com//. Before we start, let's make a little quiz, a short quiz about ClickHouse. Please raise your hands who knows something about ClickHouse. Oh, great, half of room or maybe more. Okay, who works with ClickHouse right now? Please raise your hands. Oh, a little bit less hands, and maybe my talk today will be interesting for you, maybe for other audience. Okay, and last question, who has more than 10 terabytes compressed data in your ClickHouse installation? Only one. Okay, only one happy hand. Man, you are interested person, we can talk about your setup installation after this talk. So, let's talk about ClickHouse workload pattern. ClickHouse, as a usual Linux process, uses 4 common resources: disk I/O, CPU, memory, and network. My workload pattern for ClickHouse is look like data excavator. For each query, ClickHouse allocate maximum allowable resources to process your query with maximum efficiency. This approach creates workload spikes. Many concurrent queries will struggle to sustain hardware resources. Moreover, background merges, data streaming from the message brokers, background data moves, and other background processes also allocates resources with the same time when you execute your query. My first advice, don't run ClickHouse on the same hardware with other heavy services. You can deploy ClickHouse on the shared hardware with in test and development environment, but not in production. As a general rule for planning hardware capacity, let's talk about 10 terabytes of compressed data for each server in your cluster with available memory between 64 or maybe 128 gigabytes of RAM. And minimum 32 CPU cores for these data sets. And of course, 10 gigabits network is always better than 1 gigabit network. For less data size inside your installation, use the less hardware proportions. Next slide shows us ClickHouse collect a ton of telemetry and logs inside ClickHouse itself in the system database. This system database can show us any internal aspect of works of ClickHouse. On the slide you see a short list of available tables. It's divided by the 7 groups. First group is metrics related table. It contains current metrics values and also historic metrics values. Second group is runtime related process tables. It shows us what exactly happens in right now, like current executed user queries, current background merges, current background moves, and current background mutations. The next table group is explain us how exactly works right now clusters and replications inside your ClickHouse. Next table group explain how to use your disk space and which your tables contains table structure, table column structure, and how many bytes it allocates on your data on your disks. Separate table which can store the whole ClickHouse server logs. It's with name system text log. This table allows us to make some logs analytics inside ClickHouse without any external tools. Next table group is tables, debug tables, which allow us to figure out and profiling your ClickHouse in runtime with function name level precise. Last but not least, it's tables related to which show us what exactly happens in background processes related to the streaming data from the message broker, like Kafka, or maybe streaming data from S3 or from Azure storage. Connectivity implemented inside ClickHouse in a very efficient way and doesn't allocate a lot of resources. So my second advice is always turn on telemetry and trace logs. It helps with troubleshooting. Next one is visualization of the metrics system table inside the internal dashboard in ClickHouse. Because ClickHouse stores a lot of telemetry data, it actually can itself visualize it in the simple dashboards. It looks like mini Grafana inside ClickHouse. It allows us monitor server overview metrics without any external tools. Actually, ClickHouse have an embedded Prometheus exporter, and if you want, you can of course monitor ClickHouse with Grafana and Prometheus and other modern stack which provided in your organization. But if you don't have these tools, you can use internal ClickHouse monitoring dashboard. On this dashboard, we look to the usual workloads to one of production server for the last 24 hours time range, and this server have 64 gigabytes of RAM and 48 CPU cores. On top left corner, you look to the queries per second graph. Baseline is 6 queries per second, and you have constantly short spikes to 10 queries per second. When you will observe high load here, you actually could get a long flat plateau. It means you achieve to query unit output performance in your server. On the top right, you look to the CPU usage graph, which indicates how many cores are busy right now. Actually, this is time per second which spent to CPU usage from the ClickHouse perspective, but it divided to the available CPU cores. So you see in the peak, the server can utilize only 15% of available cores. On the top right corner, you look, bottom left corner, you look query running graph. It's number of active queries which running in the same time. It's just like the metrics. Burst here would be correlated with spikes on the queries per second. But if you look to the burst here or long time look to the high numbers, queries per second graph is still low. Actually, it means you have long running queries. I mean, ClickHouse can run queries which executed less than one microseconds, 1 milliseconds. But actually, ClickHouse also run queries which continue run several hours. On the bottom right, you look to the merges running graph. graph. Its graph shows us how many background mergers executed on the same time. Next portion of graphs, on the top left, you look to selected bytes per second graph. It shows us read to output. As you look, we have some rare spikes. High values here. If it's unexpected, it actually could means unexpected bad filter conditions, or bad partition Y, or bad primary key efficiency for select queries. On the top right corner, you look to the I/O weight graph. This graph shows us how many cores is busy during our wait. Actually, it's time-related metric which ClickHouse process spent to the I/O wait, but divided to available CPU cores. So we have some spikes, but actually it's not dangerous because we have a lot of cores, and actually this is not the bottleneck right on this list graph. Next graph is on the bottom left. You look to the CPU weight. Its graph is similar with I/O weight, but measure time which spent by ClickHouse server when ClickHouse threads ready for execute, but wait, OS scanner will schedule this. If you look high numbers here, actually it should be near zero, but sometimes you can have spikes, but if you look high numbers here, it means your CPU is overloaded. On the bottom right, you look to the OS CPU usage in user space graph. This is another metric which measured from the Linux kernel. It should rise and fall in tandem with queries per second rate. If user space usage is flat, but I/O weight also is high, you should try to reduce I/O operations first instead of trying to decrease CPU bound operations. So one more graph. I will stop. I promise. On the top left, you look to the CPU usage in kernel mode. Spikes here means heavy syscalls, heavy content switches, or heavy system works. Actually, it measured a time when ClickHouse process switched to the kernel mode and execute something on the kernel space. On the top right corner, you look to the read from the disk. This graph means physical reads bytes per second. High values here, it's expectable because ClickHouse like streaming sequential read from the disk. Actually, it also means you have some Linux page cache misses, or maybe you just try to read the cold data which stored some times ago and you need aggregated right now. So on the bottom left, you look to the right from the file system graphs. These graphs measured by reading from the OS perspective, reading from the file system. These numbers should be much higher than the reads from the disk, because ClickHouse actively uses Linux page cache. And as you see on this graph, we have values around twice between read from disk and twice differences between read from disk and read from file system. It means Linux page cache works well for this ClickHouse instance. On the bottom right, you look to the memory usage graph. Actually, if this graph shows us some achieved limits near available system RAM, you actually will get memory limits exceed errors in your queries. Might third advice to decrease per query memory usage, try to enable external sorting or external grouping by operations which allow us to reduce memory usage. Or make another optimization for your queries to reduce memory usage. Okay, last but not least. On the top left, you look to the load average in the 15 minutes interval. It's it's the whole system overload graph. It shows us number of threads which wait when OS executed, measured by the kernel level, not from the ClickHouse level. If you observe high numbers here together with IO weights, it means server disk or network IO is overloaded. If you look to the high numbers here with CPU weight, it's mean CPU is overloaded. Actually, often ClickHouse can overload both CPU and IO. Actually, if you use ClickHouse in the production workloads, you can get the whole queries with 100% CPU and your disk or IO will in the limit power. So on the top right, you look to the selected rows per second graph. If you see high numbers here, actually it usually means maybe you get the whole table scans instead of sparse index of scans. On the middle left, you look to the instant growth per second. This is your ingestion rate. Bars here may often create many data paths. Data paths in ClickHouse is immutable. Once right, when we have update any one row, we need to create new data paths. And I advise you to always try to insert data with maximum batch size. Doesn't try to insert 100 rows per one insert statement. Better insert data with 1 million rows per one insert query. Okay, on the middle right, you look to the total merge tree paths matrix. Its matrix just shows us how many data paths on the server created right now. When this matrix is constantly grows, it actually means you maybe create small inserted data paths, or maybe your merge tree backlog under pressure, and it could affect on the it could degrade select performance in the near future. On the bottom left, you look to the max parse for partition matrix graph. Actually, it depends on the ClickHouse version. We have a default limit for ClickHouse near 300 or 3000 parts per one partition. Partition actually is a logical union inside ClickHouse, but when you hit this limit, new data inserts will be rejected with error too many data parts. To avoid it, actually your client should implement retry mechanism to insert to ClickHouse. And if you get too many parts errors, just try stop your ingestion and try increase your batch size. On the bottom right, you look last but not least. It's a graph. It's concurrent connection, network connection to the ClickHouse. As you see, we have a 200 network connection. It's different colors mean different protocols, different interfaces. ClickHouse support HTTP, MySQL, TCP, native protocol, and PostgreSQL, and maybe any other database in the future, which allow ClickHouse will mimigrate to the other database. Not on the SQL dialect, but on the transport protocols. Okay, next one, it's after overload to the whole server matrix. Let's talk, second part, let's talk about how to find bottlenecks on the query level. First of all, to figure out what exactly happens on the query level inside your server or inside the whole cluster, we need to clear visualization pattern for high overview. I propose to make heat maps graph from the system query log table. On this slide, you see a heat map which visualizes query execution frequency. On the x-axis, you see the time. On the y-axis, you see the normalized query hash. These numbers is actually hashes from the queries, but normalized query hash is a pre-calculated field in the system query log table when we replace inside the SQL queries our scalar constants to the placeholder and calculate hash from this modified queries. It allows us merge different queries with the same query patterns, and this allows us visualize how often we run different queries during the time. As you see, some queries have a spike, like look to the colors on the top left corner. Actually, to create this heat map, I use two tools, Rare and ClickHouse timeline. Scan barcodes on the top left corner, top right corner, and you will see the source of these open source tools. Okay, next heat map shows us combination of the error codes and normalized query hash. Actually, you see on this graph, we have some access denied errors constantly happens during the last 24 hours, and sometimes we have a syntax error, rarely, much rarely, and we can figure out, we can get exactly error messages and exactly error stack traces inside the system query log. Just make queries like select wildcard from the system query log, where normalized query hash exactly equal this number, and error code, exception code, have a syntax error. So you can make simple queries and get detailed information about your query executions. Next heat map shows us CPU usage by normalized query hash. Scan barcode and you can get the source with example SQL query with bash scripts and so Golang tools, which allow you to create heat map, something like that. On this slide you see you can easily identify areas when some queries allocate more CPUs than others. Actually, latency here is microseconds in CPU microseconds, CPU microseconds for the different query patterns. And as you see, some queries have rarely spikes, and some queries have more frequency, but some queries with areas with blue color, it's low CPU usage, but areas with violet colors, it's allocates more CPU resources, and rarely queries allocate a lot of resources, but executed rarely, not so often. Next heat map shows us memory usage by query pattern. This heat map shows us most of queries use around 16 megabytes of memory, but some infrequently queries have allocate around 1 gigabytes of memory. High memory usage queries actually often could be root cause of unstable performance. High memory usage queries can trigger memory limit exceed errors and even kill other queries. I will explain later why it happens. Next heat map shows us read bytes per second for the just read bytes, the whole read bytes by the query hash. This higher read volume here usually means but where conditions or but partition by expression or inefficient primary case usages. On this slide you see how one frequently query constantly reads around 1 gigabytes of uncompressed bytes. Look to the light violet areas. And another rare query read around 100 gigabytes of uncompressed bytes. Look to the red color bytes. I advise to find by query hash, but I advise to find by query hash and check the primary case filters, partitions by expression. You can easily get it from the system query log, just filter it with query hash field. And use the explain SQL command to figure out how exactly your query is executed. Okay, last but not least, after we look to the read bytes per queries, we can look to the heap maps which show us written bytes split by query pattern. As we see on this slide, we see one query has spike around half gigabytes of uncompressed data writes, and second query often writes around only 200 kilobytes, near 200 kilobytes. Heavy writes actually may affect selects and merge because we have a power in our I/O systems. I advise to always use the batching insert, as I said before, to reduce unnecessary background merges on the future. Okay, when we overview and found problematic query hashes, what we should do next? I propose to make flame graph from another table, system query, system trace log. System trace log, by default, it to collect data which required to create proper flame graph allows us profiling query on the function name precise. To collect data for the okay, we can extract the top queries from the system query logs and can pass it to the ClickHouse flame graph tool, which allows us to visualize flame graphs. Please scan QR code, it's linked to GitHub, where you can look to the ClickHouse flame graph tool. This tool allows us to build flame graph that shows where exactly ClickHouse spent time on the function level precise, or even where exactly memory was allocated. Okay, actually I talked about the flame graph so much time. What flame graph? What exactly is it? To collect flame graph data, we need to dump stack traces inside the ClickHouse constantly, for example, 50 times per second, and store these stack trace addresses inside the system trace log. Actually, we can now also dump stack traces on error memory allocations or deallocations. And system trace log table allows us to visualize data for the CPU time spent, real time spent, I mean CPU and I/O, and even memory allocations and deallocations. You see on this slide memory allocations flame graph. White bars here means more memory usage. On each level you see function names. I hope okay you can read it, function names. And actually on this slide we see insert query where 7% allocated for squash transformation, 55% allocated for buffer during writes to disk merge tree data, and 38% allocates for buffers during read and deserialize data from the ClickHouse native data format from the TCP socket. I recommend use the Flame Lens tool to explore flame graph interactively. Please scan QR code if you're interested. Okay. Next approach, after when we can figure out this flame graph, or maybe we don't have enough data, but actually system query log contains profile events field which collected during query execution, and we can compare slow and fast query executions, and we compare percentile values for the different queries executions. And we can aggregate it. On this table, you see, and we can compare differences between 50% percentiles or maybe 99% percentiles. And on this table you see insert query, which we choose it on the previous stage. 50% of chosen insert query write only less than 100 rows, but sometimes it writes more than 2.5 million rows. So it means actually it's not dangerous, it's normal. Different queries can write different amount of data, but you can actually ClickHouse contains documentation for each performance event. And you can scan QR and try to use ClickHouse timeline with the profile events mode. And okay, after we figure out how profile events works, how we can create flame graphs, let's talk about a little bit different about memory limiting city errors. How exactly, why exactly it happens? ClickHouse has a memory tracker. On each allocation, it checks the limit. If current memory usage hits the limit, it waits a short time. And if memory is not fixed, the next allocation will throw exception. Next allocation could happen in other queries. And these other queries could be killed because your previous query allocated too much memory. So query contains the patterns, error message, contains the patterns. When you see error message which contains 4 query, try to rewrite query and try to enable external sorting or external group by. Try to reduce max threads settings for this query, which will slow down performance, but it could be allocated a little much more less memory. Okay, and when you see error message contains for user, try to look to the max memory usage for user. Actually, this is a rare error, but in some installation, administrators can reduce memory usage for the selected users. And if query contains total, actually it means the server, the host server allocates memory near memory limit. To avoid get OOM killer message, ClickHouse try to kill executed queries or kill executed background processes to survive. Instead of restart or something else, to avoid OOM killers, ClickHouse try to kill access queries. And you can decrease max server memory usage ratio settings. But actually, if you change it, you could just get memory limits error just a little bit earlier. Or maybe you can increase it, but you can get the OOM killer event from the OS level. And sometimes your memory usage pattern from the query is slow, but background processes also allocate memory. This slide shows us a table which scraped from the 5-6 different ClickHouse system tables from the system database, which allow us grow metric-related metrics, memory-related metrics, and show it from the OS level perspective, process level perspective, also dictionaries. It's ClickHouse primitives which allow us fast hash lookups, and also spread primary case memory usage split by the database, also memory usage for the queries split by the users, and some internal buffers which allocated for the read and write files. Okay, last but not least, actually when we found problematic normalized query hash, often we need to figure out how exactly this query executed from the ClickHouse point of view. You can use explain, and ClickHouse have multiple explain options. On the slide you see simple query which have a whole table scan and get around 5 billion records. On the right part you see explain modes. First explain plan indexes show us index usages. On the indexes you look to the min-max paths 35 from 35. It means you cannot skip the data path during scanning table because you don't have where condition. And on the second part you look to the explain pipeline results. This explain mode show us transformation tree. On the bottom level you look to the merge tree, select from the read data from the disk in the 32 threads in parallel. And after that we have aggregating also inside the 32 parallel threads. When you look to the reduce on the query execution tree, it means your queries cannot be parallelized to calculate your requested data. And last but not least, it's explain estimates. It shows us numbers, how many data parts, how many rows, and how many primary case mark files readed to get your query data. Okay, scan QR code on the corner and try to use ClickHouse timeline utility with explain mode. So this is all from my side. Merci Shaq. Thank you for your attention. Спасибо. You can contact me in Telegram. Also, attendees hiring. Scan the second QR code if you professional C++ programmer. Please ask your question.
You mentioned some queries could be running hours. What's the use case for those queries to be running for hours, if not days? You mentioned at the beginning.
At the beginning, do you mean queries for the create heat maps or queries for the user level?
No, just no clue. I just was listening to your presentation, and you mentioned some of the queries they will be running hours and hours, and I'm just thinking, what's the use case for this?
Okay, for example, you need example of queries for the long-running queries for the hours. Okay, usual queries which try to in attach. Usually you could create a reporting for the something like cross analytics for the data sources with the long time period for the funnels. So you have a raw data and you need to aggregate it, and actually you can get data from the different data sources, and some data will late than other. And you cannot aggregate this data, and you need to create marketing ROI for the marketing sources, for example, every day. And if you have high traffic, you will get the long-running queries in ClickHouse, even in ClickHouse.
Right, good. I was thought if a query runs longer than a few seconds, then that query needs to be killed. That's why I asked. Thank you.
Okay, but for ClickHouse use case, ClickHouse can run short queries, and actually at the same time it can run the really long queries. So maybe another question, guys. Don't be shy. Any question will help.
Thank you. I have one question regarding the formula you showed with percentiles. I'm just curious, is there any mathematical base why you choose this formula? It just works? Where it comes from this 99, 4, 50, or?
You mean percentiles? It's just okay. It's just mathematical. It's just a statistical. It's formulas for the quantiles. From percentiles and quantiles it looks similar, but actually I miss this terms. So this is usual percentiles which we use on the operations. We can just when you look to the median 50 percentiles, it show us usual matrix value. When you look to the 90%, you look to the outliers. But when you look to the 99 percentiles, you look to the maximum available values. So I think it's enough to think about spreading of the volume of the matrix value.
Okay.
So, next speaker. I don't see any hands. Maybe short break. Thank you guys.